Okay, my friends, I am excited. This is Sabine Hosenfelder, and she says, today I present the 5 biggest physics mysteries according to me, which is according to her. Now let's see what she has to say. And can Roger solve any of these? Well, Roger says he thinks he can. Let's see what she has to say. And I'll stop this as we go along just to make sure that you understand what she is saying.
Hey, I present the 5 biggest physics mysteries, according to me. Number 5, Einstein's theories don't forbid faster than light travel.
All right, can we go faster than light? Hold on. That's one thing. Obviously, that's an easy one to understand. Can we go faster than the speed of light? I think we can.
Well, we just don't know how to cross from speeds below the speed of light to above. Is it possible? And if so, how? Number 4, time seems to have a direction. We know that that's because entropy increases, but that...
All right, this is one that time is, it incrementally goes forward. There is no going back in time that I can understand. Time just continues. All right, so that's my opinion on that. And there is no way to deal with that one, so let's go on.
Means the universe must have started out at small entropy. What?
I do want to talk about a video that I am going to be doing. It's going to be called The Big Bang, The Big God, or The Big Mystery. And all of those things I think could be true, because everything came from somewhere. I mean, it had to come from somewhere. So everything in the ancient texts talk about God, and everything I have found supports that evidence. So, you know, there's a big mystery, though. Where do you go after you continue on through this realm? So that's kind of tricky. So she's asking about that.
Why? Number 3, just what's a measurement?
All right, measurements are arbitrary. You know, some people use millimeters, some people use inches, some use, you know, that type of thing. It's just a distance, basically a distance or a quantity or, you know, some measurement, some amount. Basically, that's that.
Physicists say if it measures something, we call it a measurement, but that doesn't explain anything. Number 2, Coitus' formula is the relation between the masses of 3 elementary particles.
I can do that very simply. And there isn't 3 elementary particles, there's only 2. And that's the electron neutrino and the muon neutrino.
Electron, the muon, and the tau, that comes out 2/3 to an accuracy of 5 digits after the point.
Okay, I can tell you. Well, anyway, we'll go. I'll be explaining all this in detail.
I don't think so. Number 1, just why do things have units? Time, length, energy, mass. What are they?
Well, that's another thing that's just sort of kind of silly to speak about. Everything has a unit measurement. It's like in a periodic table. Each one of these is stable at a certain point. A unit would be some form of a stable thing. You can assign inches as units. This is an inch, this is 2 inches. That's just division of distances. That's all that is. These are truly units. Because hydrogen in the atomic model that I have, which is correct, by the way, a hydrogen is 1,825 or so dipole electrons, and each one, as she asked about how much things weigh, each one of the hydrogen dipoles weighs approximately 0.0005854, something like that, atomic mass units. Well, all you do is take 1,823 particles, would take 1 and divide it by 1823, and whatever that number is, approximately is what one of the dipoles is. And this is what a proton looks like. It doesn't look like this and have a couple of quarks in there and so forth. It's 1,823 dipoles. And the dipole flood theory here on the internet is the atomic model of a proton. This is it, what it is. And all of the dark stuff goes right to the center, and this is all coated with white around it. Anytime you get to the atomic level, which is here, all of these are completely coated with electrons, so we can never see inside to where the dark matter was. It's like this. You're looking for the dark matter, you can't see it. It's inside. And all of the white is surrounding it. And it bounces back at you. That's the whole idea. That's why it's right in front of us. We just never realized it was there. Everything weighs something. How do you think it weighs something? The dark matter is the only part that has a weight. The white has virtually no weight. And that's exactly what they say at Fermilab. It shows the same particles we found, identical same particles. And it says the black one has all the weight and it has all the mass. The extended particle, the black one, is a fixed size, never changes. I agree with that 100%. Has a fuzzy edge around it. I agree with that 100%. The point-like particles are mathematical extractions, zero size, have virtually no weight whatsoever to them. But they do have a field, an energy field surrounding something. There has to be some weight to them. Like the only thing I can equate it to is like a soap bubble. So that one there is just a fixed one, never changes. That one's going to be like this. The one down here is going to be fluffy or get small or big or whatever, but it's like a balloon. And with maybe like a very, very, very fine skin around it, basically, which is the field. But what is the field constructed of? It's magnetism. It's magnetic. And when you bash into it, it glows. It's like taking a balloon and popping it. Something like that. That's the only thing I can equate it to. Okay, I'm going to try to make this not too long. This is the particles that Fermilab has found. That has all the weight, and this has all the energy. And this one never changes in size, and I show this in our experiments, which are right here. This is, again, the Fermilab particles, and these are the ones we found. They say they have a glowy edge around them. Absolutely. They never change size, the black ones. The two black ones, they just never change size. Now, when they are together like this, they're just like two-bar magnets. However, when we put that through the Venturi, it accelerated and exploded and created electron showers and muons, sterile muons. And here's what it looks like here. What we did, here's what happens. You take the light, all right, that's a pulse red laser, and it's just beginning to accelerate now. All right, so it's just beginning to move forward. That's why it's getting glowier out here. Now, this is the leading tip of it. We headed it towards the Venturi, and when it got into the influence of the Venturi, it had to accelerate. And the particle itself, which I'll show you in a second, is pulled directly out of the wave. Do you see that? And then here it exploded. This is a subatomic nuclear explosion. That's what it is. And here's what happened at the Venturi, and here's what happened during the particle's procession towards the Venturi. Here's what happens. Here's the particle heading out of the wave. Here it is in its neutrino phase. Neutrino means it's got energy, but it's not really full energy. And then it's another energy level over here. See, sideways this way and now that way. These are the ones that are fully formed photons. And the reason they're fully formed is because they are being bashed back against so hard that that's when they make their bubble effect and they show up as photons. But it has to be that concussion backwards to bounce back against creating light. That's what these particles hit, and they bounce back creating light. Here they think they hit a wall, and that's why you see them so perfectly. Now and that's because of the bounce back, and that's this wave right here. Where is it? Here, right here. I don't know if you can see that or not. Let me see if I can focus in on that. You see that wave going backwards? You see, that's not supposed to happen. That's what's called reverse EMF, electromotive force. And that's a bounce back wave created by this subatomic nuclear explosion. And that's exactly what it is. You would never even see these light particles, which are coming forward. They're all over the place. They're everywhere, moving this way because of that laser. But you never saw them because they're not accelerating or they're not being pushed back at. Here they are being pushed back at, so they pop up. This one's being accelerated forward. But here it shows up similar to these. And at this point, it's all, the game's on. And luminosity means energy. There's no reason we shouldn't be able to harvest that energy right there that I can't think of. All right, that's electron showers. These are sterile muons. Let's look at them closely. Now, I'm doing this for Sabine. I hope she watches this because she's asking for these answers, and I think I have them. This is the muon neutrino attached to the electron neutrino, what's called a Dirac neutrino. You see the black and white? Right. A Majorana, I think, must be the neutrino phase. It's not quite a Dirac, which is really the black and white. So we're looking at, in our experiments, the true black and white. Well, here it is right here. These are two Dirac neutrinos back to back, just like bar magnets, to create a stable photon. And that photon has a big round field around it. It's a magnetic field. You know what magnets are. You push them together, you can feel them. That's what the field is. And that's why they bounce. It's just like it's got to be some kind of a balloon effect. I mean, that's all I could tell you. That's all it just seems it's got to be. Now, I showed you that those particles, black and white. Here they are here. The green is the same thing. No difference whatsoever. And these are the neutrino phases. Remember seeing these little particles in the red? Same thing. But the red is much faster. I'm sorry, the red is much slower. The green is much faster. And it's the spin that's faster. And I can show you those both going at the same time through the same venturi, and the green is much more powerful. And the blue is here slowing down, coming through hot. You can't even tell there's two particles. But as it slows down, you can see there is two particles. So that's slowing down light, and this is accelerating light. And there's no other way to see it. Not only that, this is fission, and that's fusion. And there's no other way to see that. Because when they were coming out, they would look like this. That's the particle, and that's the one where it's enhanced to show the energy levels. And you can see that the forward leading one is concussing with all these little red dots in the front, because those are nothing more than gases and electrons that are floating in the air, charged particles. And then when they hit the venturi here, they just exploded and created the muons and electron showers. And here it is, really up close. Look at this. This is these coming in. Now there's a venturi which brings this down into a tiny little slit. And because all these fields are crushed now, and the black is slapping it, and I mean it does, it slaps it. And because of the design of this particular venturi, there's nothing allowed other than a white through. And the only reason we see the black is because it sits on top of the white. So we broke it away here from the white, so that's sterile muons, electron showers, and then the black just tries as hard as it can to get back. This is what the strong nuclear force is. These are nuclear particles. These are subatomic nuclear particles. The only reason we see the black is because it's sitting on top of the white. The black is cold, absolutely cold. It gives off no energy whatsoever. It's attractive only, and it doesn't care. It's not repulsive. The black does not repel other blacks. They sit right on top of each other. It doesn't matter. And so they form a dark center surrounded by the white particles. When you're in this region, there's only, this is as small as you get, so you can see them very easily. You can see what they're made of. And they're made out of the black and white together, one here, one like that. A single one, in other words, an electron would be this right here. An electron would be that. And that's not going to be stable. It's not stable. It's not like light. Electron is not like light. An electron either wants to stick to something else as like something that just hangs off as a charged particle, or it wants to incorporate into something as heat and bring the heat level up. But it's still hanging around inside. It's just not like static. All right, that's all heat is extra electrons. Even the more electrons you put in, the warmer something gets. And guess what? The warmer it gets, the heavier it gets. The only thing that gets lighter is gases because they expand. You heat something up, like if I took my buddy here, Caesar, my goose, Caesar Augustus, and if I heated him up, he'd get heavier. It wouldn't change. There'd be no difference whatsoever to him. It'd just be there's more particles that are heat particles. These are heat. And they would be in there and they would warm it up. And then if it was put, that warm thing put into a cold environment, those particles would seep out into the air to warm the air up. That's all heat is. The heat is just an exchange of these particles. That's all it is. And it's these particles here. All right. The light, I suppose, would do basically the same thing, but basically it's excess electrons. When you turn your heater on, it just runs the electrons through, the electrons pump out into the air. Basically, that's how it works. So I think I've shown a pretty good case to say that these are the particles they found in Fermilab and CERN, no difference. And we found them here, but we use light instead of big, huge balls of particles. When they smash things, they get all this kind of nonsense everywhere. And then they dig through and we found something like this and like that many, many, many times, the smallest things we've ever found. So they must be the smallest things. And yes, I agree with that. They probably are, because we started with light. And then we split them apart. Fission, fusion. Light accelerates, light slows down, light's a particle, light creates a wave, it's all right there in front of your face. And the black particle is dark matter and it's gravity. It solves virtually everything. Dipole electron flood theory is the way. All right, so don't forget, that's Fermilab, that's not me. I'm not making these statements. And they're also making the statements about the quantum foam, that the space is not empty. Empty space isn't empty. It's saturated with particles. I mean, they're everywhere. And this is my theory right here, dipole electron flood theory. That's what the nucleus looks like. And I believe it's just a completely black core surrounded by white particles. There is one other possibility, and I show it here. They could be layered, but I don't think so. I think it's this one here, where it's just black in the center and white, different colors, because the tightest ones are going to be in the blue range. The next layer out is going to be in the green range. The next layer out is going to be in the red range. It's just the further away they are, the less tightly held they are. When the blue goes, it's gone. When the red goes, it sort of doesn't go, it's not as tightly held. All right, so when you get down to where you're breaking off the blue bits, you're really down. Really close to the nucleus. That's why hydrogen explodes so much, because that's the only particles you got is the ones surrounding the core. You're right down there in the blue. You ever hear hydrogen go off? It's unbelievably loud, because every particle separates from every other particle. You end up with 1,823 of these. And I imagine the blacks and the whites separate and you end up with these too. I don't know. But when that nucleus goes off in a hydrogen explosion, you need oxygen and hydrogen together. It's just an enormous explosion. Now don't forget, I showed you the light. It comes through the air and it pushes everybody else in front of it and makes them glow. So this is the real pusher, and these are they shove back. I call it push to shove. So that's why you see that there. Now, this is the acceleration, and that's the actual particle. And here's where it concusses against itself because it's bouncing back. It feels like it's hitting a wall right here. That's why it's turned into a white, glowy particle right there. And everything explodes at this point. You have fission and fusion, and this is complete separation of power. This proves that the black slaps the white. You see it? It's slapping that white through there. And when when no black can get through the Venturi, only the white gets squirted through. And that's what the other Venturi did right here. Only the white can get through here. So if we could harvest it right there, that's what you want. This is the stuff that makes your car run and makes all your electricity work. The black is all the weight. And when you charge a car up, it doesn't gain any weight. All it gains is the white. The black stays out. That's the whole idea of generating electricity. You're generating white and keeping the black away. You charge your car up, it weighs 4,000 pounds, empty. You charge it up, it weighs 4,000 pounds. It gains nothing. You drive it all day long, you come back, it still weighs 4,000 pounds. Doesn't matter. It has no weight to this energy. And I can show that in a nuclear bomb blast. It's very simple to see. The house just smokes up like this, not even anything even moves, just all the combustibles smoke. And then a second later, the whole house goes. That's when the black catches up with the white. Just as we see in this other, right here. The black, first of all, the white would burn a house up, and then that would knock it over. And anything that's combustible, people would vaporize. Anything that is combustible, this invades it so viciously that they just smoke. But no movement. It has no mass. It's just some kind of like a soap bubble bubbling up. And then the mass is all in the black. That's where your mass is. That's what your gravity is. That's your dark matter. It's your muon.